We are at the end of this chapter talking about cycloalkanes, and we will very briefly talk about cyclopropane, cyclobutane, and cyclopentane, and then we will talk about cyclohexane in detail. So about cyclopropane, and first of all, let's remember that cycloalkanes, their formula is CnH2n. So cycloalkanes have two less hydrogens than their related alkanes, the straight chain alkanes. So for cyclopropane, we have C3H6. In this model, in my molecular model, I haven't shown the hydrogens, but you can guess that two hydrogens are attached to each carbon. And you see, because of the size of the ring is too small, so you see the bonds are kind of bent. So cyclopropane is extremely unstable and it's ready to pop open in the reactions. But what if we add one more carbon to cyclopropane? Then we have cyclobutane. Its formula is going to be C4H8 because CnH2n. So as you see in the molecular model, three of the carbons are, I don't know how clear it is, but three of the carbons are in one plane, but the fourth one is kind of like puckered up. So these cycloalkanes do everything as far as their shape to eliminate the steric strain they have. So that's all you need to know about cyclobutane. The last carbon, the one of the carbons is kind of like, maybe it's not showing here well, but one of them is kind of like puckered up to eliminate the, don't forget, each carbon has hydrogen. So the fourth carbon is going to be puckered up a little bit to eliminate the hydrogen-hydrogen interactions. If we add one more carbon, we will have cyclopentane. Four carbons will be in one plane, and you see the fifth carbon, this one is puckered up a little bit, not completing the same plane. Again, the same reason, the hydrogens here, their effect must be, the steric strain must be minimized. So that's why this fifth carbon is about to be bent a little bit. That's for cyclopentane with the formula of C5H10. But our focus of our study here is cyclohexane. Why? Because a lot of biomolecules like carbohydrates, cholesterol molecule like estrogens and starch, and many more biomolecules have a cyclohexane shape. So let me add one more carbon to my molecular model, and its formula CnH2n is going to be C6H12. Again, two hydrogens to each carbon. So for cyclohexane, it's not flat because you have two hydrogens to each carbon that I have not shown because it would be a very crowded molecular model. But two conformations are assumed, two type of isomers we have for cyclohexane. One of them is called boat. Four carbons will be in one plane and two of them will be puckered up. So they will take the shape of a boat like this. Doesn't it look like a boat? Okay, so there is a strain between the hydrogens here, right? me the hydrogens real quick. So in the boat, you see the two hydrogens have a steric strain. So boat conformation is not very stable for cyclohexane. This is boat. Cyclohexane boat is not stable because of the steric strain between the two hydrogens of carbon number 1 and 4. But in order to minimize the strain between the two carbons, instead of have a boat, we can have a chair conformation, just like a chair. It has a back, it has a foot section. So if we keep it for the back and turn this carbon down as if we have the foot part of the cyclohexane, it's a little bit hard to work with this model. Okay. Doesn't want to turn. All right, so you see, now your hydrogens are as far as possible from each other. There is no steric strain between two. And again, don't forget that to each carbon, there are two hydrogens attached. So there are 3 hydrogens to the top. Let's first learn how to draw cyclohexane chair. There are 6 carbons, right? So put 2 wedges, one on top, one on the bottom, and then we are supposed to put 2 parallel lines and we connect them to the wedges. So 1 wedge on top, 1 wedge on the bottom, and the 2 parallel lines should be connected to the wedges. You can number for this just cyclohexane without any substituent on it. You can number any of these carbons as carbon number 1, but since this is the skeletal structure, you do not see the hydrogens. So let's start from here. This would be your carbon number 1. This would be carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6, because we need 6 carbons in cyclohexane chair. And we can also have another chair. What if instead of this conformation like this, we have this conformation? So the top would be on the other side and the foot is on this side. So you put the wedges again and draw 2 parallel lines, not very straight. This one was a little bit straight, so yeah. This one is a little bit better. So you can number again any of them. 1, 2, 3, 4, 5, 6. You can start from here, you can start from here for just a simple cyclohexane. What is important for us is, let me see if I can make more hydrogens attached. So what I'm doing is to connect the hydrogens every other carbon. So this carbon, not this one, but this one, And not this one, but this one. Okay. And now go ahead and connect the rest of these hydrogens, which are called axial hydrogen. Axial. If you consider an axis going through a perpendicular axis going through the middle of the molecule, the hydrogens which are parallel to this axis are called axial hydrogen. These hydrogens cannot be all on top or on the bottom on every single carbon. Every other carbon, they are on top 1, 3, and 5. As you see here, if we say this is first carbon, 1, 3, and 5. Why? Because of the steric strain. And if you are holding an actual molecular model in your hand, you will see the holes for axial hydrogens are up and down every other carbon. So these are all the axial, hydrogens. So there are 6 axial hydrogens, 3 of them I'm missing 2 more. 1, 2, 3. All right. You see, 3 of them are on top and 3 of them are in the bottom. So if, for example, you have 1, 3, and 5 on top, you have 2, 4, and 6 on the bottom. Now, the axial hydrogens cannot be all on top because of the steric strain. So you have 3 axial hydrogens on top, and then 3 axial hydrogens, 2, 4, and 6 on the bottom. What is important for our cyclohexane carbons? We call them up carbons and down carbons. So the carbons which are to the top of the molecule, they are positioned up, they're called up carbons. Here 1, 3, and 5. So what you see on the up carbons, the axial hydrogens are also on the top of the molecule. So for up carbons, you have up hydrogens, up axial hydrogens. Look at the down. Down is 2, 4, and 6. It looks like they're all towards the bottom of the molecule. So down carbons have down axial hydrogens. That's what you can refer to when you are drawing your cyclohexane chair. So you have 3 up carbons, 3 down carbons. Every other carbon, they repeat. On the up carbons, you have up axial hydrogens. What are axial hydrogens? The ones that are parallel to the axis of the molecule. Then on the down carbons, you have down axial hydrogens drawn to the bottom, towards the bottom of the molecule. Now, I'm not done yet. This molecule has only 6 hydrogens. I need 6 more hydrogens on it. So if I, let's see. I'm using a different color bond, as you see, to distinguish. One, two. All right. Now, look at the rest of the bonds, the colored bonds. You see, they look like a belt around the molecule. Do you see them? Axials are up and down, right? The white hydrogens. And the purple bonds, they look like they are like a belt around the molecule, right? So they are called equatorial hydrogens. Equatorial hydrogens. So on each carbon, you're missing one bond, right? So you need to have equatorial hydrogens. Let me erase this. Now, how to deal with equatorial hydrogens? How to draw them? The goal is to keep the hydrogens away from each other as much as possible. So, if on the up carbon, like this carbon, axial hydrogen is on top, so your equatorial hydrogen should be towards the bottom. You see, like let's say, imagine this is the carbon. You see the axial on top, but equatorial is going towards down to keep these two hydrogens away. I just didn't put the hydrogens here. I didn't want to get confused. I want you to focus on the color of the bond. On the down molecule, axial is on the bottom, so its hydrogen will be on the top. You see, down axial, the equatorial is towards up. I don't know if you can see it. The same thing. Now, up carbon, axial is up, so equatorial is down. Down, axial is down, so equatorial is up. Up, axial is up, so equatorial is down. And down, axial is down, equatorial is up. That's how you draw your axial and equatorial hydrogens. If you still didn't get it, pause the video, go back and try to start with, I would recommend, that's what I myself do. I recommend to start with the axial hydrogens first and then do the equatorial. Okay? All right. The next thing is that we need to know that we can have two types of chair conformation. I told you we can have this, or we can have if you can change this to this, it's called ring flip. You flip the ring flip. Okay? So I'm just focusing on two hydrogens here. All right? So let me remove the rest of these white hydrogens to avoid confusion. All right. What you see here in this chair, this is a chair conformation. You see an axial hydrogen up, right? This is the axial hydrogen, right? I put A. On this one, on this carbon, right? This was the high, this was the down. You have an equatorial like this, right? So look what happens when you flip the ring. Flipping the ring means put the back part down and put the down part up. Now, a little bit challenging to work with the ones, but we got it. All right, so you see, this is the up carbon now. What happened to its hydrogen? What's happened to it? It was equatorial, right? But now you see it in the axial position. If you want me to color code it, this was equatorial. Now this is an axial. And what just happened to our axial? You see, it changed to equatorial position, equatorial up. So now our hydrogen changed to equatorial. So by ring flip, axial changes to equatorial and vice versa by ring flip. That's important to know and how to determine and recognize them. That's very important to know. And then let's see. Okay, the next thing you need to know, let's work on page 18. Page 18 has a practice for us. Before we move further, let's make sure we know about axial and equatorials and the number of carbons. It's been numbered for us like this. In part A, we are supposed to put an axial CH3 group at C1. At C1, we need an axial CH3. It's a down carbon, so its axial goes down. We also need to put an equatorial OH on C2. C2, it's, wait a minute, C1, okay. CH3, sorry, my bad. This is for carbon number 1. CH3 is an up carbon, so carbon number 1 is an up carbon, so CH3 goes to the top. My bad. I have to modify. Equatorial OH on C2. C2 is axial goes down, so equatorial goes up. On C2, you need an OH. So that's how you work on part B and C. That's about the cyclohexane without substitutes so far. Now, let's work on the substitutes. What if we have one substitution on our cyclohexane? Monosubstituted cycloalkanes. Let's say we want to determine stability first. Let's say we have this and we have a CH3 on one of the carbons and another same exact chair conformation, but CH3 is on the equatorial position. All right? We want to determine which one is more stable, which one is less stable, and why. So, let me show it with my model. First, we say CH3. This is the molecule, right? CH3. All right, on top. Now look. It's in the axial position, right? Axial. Let's look at the other axial positions. You have Do you see the other axial positions? This hydrogen is on axial, the rest of them are also on axial, all on up carbons. So what happens here, you have an axial hydrogen here, and you also have an axial hydrogen here. They all will have an interaction with each other. They will have some strain with each other. It's called diaxial interaction. Diaxial interaction. So basically when your substitution is on the axial position, either up or down, it will have an interaction with other axial positions and will create diaxial interaction, makes it unstable. But let me change the CH3 to its equatorial position. I'm still working on the same conformation. So does this, or let me ask, can this equatorial position have any interaction with the axial? No, they're far away from each other. So which one is going to be more stable? Of course, no diaxial interaction, because other axial positions are still here. No diaxial interaction, and makes it stable. So you just need to look for the stability of monosubstituted. When you only have one substitution, you need to look at the interactions. At the end of page 18, you will have a practice about it. I will work on part B. Look at part B. What are we supposed to do? We are supposed to draw a second chair conformation for each cyclohexane and then decide which conformation is present in higher concentration in equilibrium. Higher concentration in equilibrium means it's more stable, so it can stay longer, right? So, oops. This is Cl. It's in axial position, right? What just did I say about axial positions? It will create diaxial interaction, right? So, if you want to change it to another chair conformation, you can change that Cl, put it on the, excuse me, on the equatorial position. So which one is more stable? No diaxial interaction, right? This one is more stable and exists in more concentration. And we have one more thing about disubstituted cyclohexanes. Light. Yes. All right. For disubstituted cyclohexanes, before we work on the cyclohexanes, before I just work on the chair cyclohexane, let me tell you, in general, I'm sure you in general chemistry you had it. When you remember the wedge and dash, wedge means both on your, towards your face, like let's say both are chlorine. Or if both of them are on dash, means both of them are away from you. That's what we just showed, a flat two-dimensional structure for cyclohexane. Both of them are called cis. When the two substituents are on one side, either towards you or away from you, we call them cis. But if they are on two opposite sides, or you can have the other one, right? As if like you are flipping your molecule. One of them on wedge, one of them on dash, then you call it trans. So substituents on one side, either to the front or to the back, it's called cis. The substituents are on different sides, one to the front, one to the back, they are called trans. The same concept for cyclohexane chair. Let's say you have so look, on the down carbon, our equatorial must be to the top, right? Because the axial is down. And here you have an axial, this is equatorial. This is an axial, on the up carbon is up. And its equatorial hydrogen is on the bottom. Up and up, right? Didn't we just say when the substituents are on the same side, it's called cis? When they are both on up. It doesn't matter if they're axial or equatorial, but both of them should be on the same side, or either up or down. So this is called cis. Or if you have this. So let's see. This is a down carbon. Its hydrogen is down and its axial, equatorial is up, right? This is equatorial and down, up, down. So two opposite directions is trans. So one more time. It doesn't matter if we're talking about an equatorial and an axial, or both of them are equatorial, both of them are axial. What matters to us is that they're both on either the same side of the ring, they're both either up or down, up or down, or they're on the opposite sides of the ring. Now, I will work on only one of these practices on page 20. This video is becoming very long. Let's work on C. We're supposed to determine cis or trans. Okay, now this is up, right? Bromine is up. So let's not just label them as axial or equatorial, who cares? We just care about up or down. And this bromine is down. So is it cis or trans on opposite sides of the ring? I'm sure you would say trans. Let's work on A also. A is a good example. So we have an OH here, and its hydrogen is up. We have an OH here, and its hydrogen is up. So OH is down, right? And this one is also down, both on the same side. How would you label it? Cis. For the next practice, you pay attention to the wedges and be careful about elimination of diaxial interaction. It says they're all on wedge, right? It says draw the structure below in its more stable chair conformation. You see they're all on the wedge, means they're all towards you. They're all cis. So you can flip them as one of the suggestions that I would do is to keep it the same and keep this one also like this. That's one of the suggestions. All right, you don't yeah, we will talk more about oxidation of alkanes and radical substitutions later on, so you can ignore it. 1 and 3 diaxial strain, you have a table. If you need any of these tables and strains and calculations, they will be given in the exam. Good luck.